Good morning, everyone. Welcome to the 49th episode of Gyaniki Tech Talk. Our speaker for today, Mr. Bhaktha Keshavachar, born in Bangalore, and the city was still clean and livable. He obtained his primary and middle school education from the local government school in Bangalore, high school and college in St. Joseph, and obtained his engineering degree from UECE. He later moved to the US, got his MS from Arizona State University, and worked at Intel for a decade. Bhaksha has moved back to India and has been a serial entrepreneur since then. Desperate to put a Made in India tag on a product, Bhaksha has led the architecture and development of the flagship mobile payment product called EasyTap, involving hardware design, mechanical design, firmware development, mobile app development, and server application development. EasyTap is now a recognized brand in the enterprise mobile space. As you transition from a hydrocarbon-based energy economy to an electron-based energy economy, the prime mover, the electric motor, has to become more efficient and sustainable. Today's motors are either grossly inefficient or have rare earth dependencies which make them unsustainable. Mr. Bhaktha founded Chara and is now building rare earth-free, hyper-efficient, and simple, robust motors for various applications. To decompress, Bhaktha does barefoot long-distance running and occasionally rides his bike in the weekend. Please join me in welcoming Mr. Bhaktha Keshavachar, founder and CEO of Chara Technologies. It is a pleasure to have you today with us, sir.
Hey, thanks. Thanks for the warm introduction. I do like riding my bike whenever I get time. Okay, cool, great.
Yeah,
Okay, thanks again. Good morning to everyone. Welcome to the talk, and appreciate your taking your time off on a Saturday morning or wherever you are. To come and listen to this and try to make it as interesting and useful as possible. We have named our company Chara. Chara stands for motion in Sanskrit. Like Charaka. The reason for this is a lot of things have changed in the past a few decades, especially in the last 2 3 years because of the raging pandemic. But one thing that has not changed is the need for motion. People still have to go from point A to point B. We still have to run our fans, run our compressors, run our motors. That thing has not changed. If anything, it continues to increase. And we at Chara want to be in the middle of that, enabling the motion in a sustainable fashion. That's why the name Chara. The broad context on which we have based our company is that the world is finally moving away from a hydrocarbon-based energy economy to an electron-based energy economy, to an electric economy, basically. The reason is the reasons are the following. One is we strongly believe that we are nearing the tipping point of a climatic Armageddon. Depending on whom you speak, it will happen next decade, next century. But we firmly believe that we have screwed up the environment quite a bit, and we need to do something to prevent it and potentially reverse it. And but we need energy to maintain our way of life and our standard of living. The one option is, it's not the only option. One option is to go electric. Why electric? Is electricity as a source of energy is easy to generate, easy to transmit, easy to store. Last but not the least, at the point of consumption of the energy, it's completely pollution free. Unlike a petrol engine, at the point of consumption, it actually emits noxious gases. Electric motor or an electric heater is completely pollution free. Therein lies the attraction of electricity. And in the long run, if we do things right in this planet, electricity is a renewable source of energy. If we use wind, solar, and according to some people, even hydroelectric, which is renewable, the rains keep refreshing the dams every year, or even nuclear. we will be in a far better position to combat the climatic change that is happening. So these all good stuff. But to enable this, at the core of this transition is the electric motor. The prime mover, which moves our vehicles, our fans, our compressors, our motors in the industry. Everywhere there is motion. Now this needs to become sustainable and efficient to make this transition successful. And if we do this, we will have a lot of benefits, savings, a lot of electricity, amazing amount of emissions. Now, why this amazing amount of emissions is half the electricity we produce today on this planet is consumed by motors. And even if we change the efficiency of the motors a little bit, let's say pick a number like 10%, we make them 10% more efficient. The amount of energy we save is massive. You might have seen a transition similar to this, or we have seen a transition. Sorry, we about in the last few years or the past decade, we have switched from incandescent lamps to energy efficient LED lamps. Just this transition is saving us terawatt hours of energy every month. The same thing will happen in motors. Move to efficient motors, and we'll see amazing amounts of cost savings, emissions, and better environment. But there's always a but. There are two kinds of motors that are prevalent in the world today. One is the induction motor. Most of you must have heard about it. About 100-year-old technology, very well established, but it's about 60 to 70% efficient. These are found in our homes, offices, industries, everywhere. The majority of the motors are induction motors. So these are about 60 to 70% efficient. That means a third of the energy we put in is wasted as heat. Now, this is environmentally unsustainable and economically unsustainable. We need to fix this. There are efficient motors today, and they need permanent magnets. They are primarily used in electric vehicles and other high efficiency products. They are usually called BLDC or PMSM motors or some other variation of it. Again, well-established technology, high efficiency, high torque, but they need permanent magnets, and the permanent magnets need rare earths. So rare earths are these 15 elements in the periodic table, which are extremely critical as we transition to the electric economy. The rare earths have a few problems. They're expensive. They are unevenly distributed over this planet. The process of mining and extraction is environmentally hazardous. Last but not the least, one country, our neighbor, China, has like 90% control of the supply chain, which leads to a lot of supply bottlenecks, geopolitical outcomes, and bunch of other things. So we need to build efficient and rare earth free motors to make this transition to electricity successful. And that's what we do at Chara. Basically, we build rare earth free, robust, and sustainable and efficient motors. We use the technology of reluctance motors, both switched and synchronous reluctance motors. Very, very simple to construct, just copper and steel, very cheap. They can operate at higher temperatures, all the good stuff. So if it's all so good, why are reluctance motors not there in the world? Incidentally, the original paper and the original idea goes back to like 200 years. I think when man invented magnetism and electricity, or understood more about magnetism and electricity, the original paper goes back there. The problem with the reluctance motors today is they're very difficult to control. They are highly non-linear machines. They have other issues like torque ripple and noise and vibration, which make them not suitable for many applications. As you folks all know, when you think of electric motors, you think quiet, you think efficient, you think smooth, all those. But reluctance motors are none of those, the current generation. And the power density is also not so good. For the same torque and power, the reluctance motors will be bigger and heavier. So what we have done at Chara, the three of us founders, and I'll do a quick introduction. Over the past 3 years, We have done fundamental R&D both in the motors and the controller. A controller includes the hardware and the software. So we have built and developed motors with fundamentally new IP, which makes the SRMs a reality, both switched and synchronous. So we have built the one of the HVAC motors that's called the NEMA 48 blower switched reluctance motor. This is as quiet as a BLDC and PMSM motor, as tested by the customer in an anechoic chamber. We also built the world's first rare earth-free hub motor. We are building this for one of our customers. We did a field test a few weeks ago, and we did some propaganda on the LinkedIn. So if you quick look at the motor comparisons, the middle column is the BLDC and PMSM. They are kind of the gold standard in terms of efficiency and power density. So our motors are this in the black, in the blue square, SRM 2.0, the new technology, and the SynRMs. So we will be as efficient as a BLDC and PMSM motor, no compromises there. Our cost will be 30 to 40% lower because we don't use magnets. Magnets are expensive. So if you look at a motor, there are three materials that go into the construction of the motor. There is steel or aluminum, and copper and magnets. So steel is about the kind of steel we use in motors is about 100 rupees per kg today. Copper is about, I think, 1,000 rupees per kg. Magnets are about 9,000 rupees per kg today, and with all the other strategic dependence on foreign countries and all that. So we avoid all of that. Our drive cost is about the same as a BLDC or a PMSM drive. We will be about 10% heavier and or bigger than a PMSM motor. That is true. I mean, nothing can be obtained for free in this world. So we give up the powerful magnets. We have to put a little bit of more of copper to create the flux. So we will be a little bit bigger and heavier, and we do hope that as we put more R&D into this, we will find ways to make this better and better, make this 10% approach 0%. What we build at Chara is the motor, the drive, and the software. It's an integrated, highly optimized, integrated solution. Everything is done from scratch. We start with the electromagnetic simulations, magnetic simulations, thermal simulations for the motor. We design, we simulate, and then we actually build the motor. We also do the design of the drive and the control software. So we do package everything in one unit and give it to our customers. So the only interface is power and control. Control is like controlling the speed of the motor, a throttle or a switches in case of HVACs. And of course, we will provide whatever interface the customer needs, whether a CAN bus, a serial bus. Since we do everything in-house, whatever interface you want, we will always provide. One of the customers wanted an IoT module on the controller so that he can constantly monitor the performance of the controller. We can do that. So that leads into the segues into the next one. We are building an intelligent motor platform. So basically, what we do is we create a model of the motor we supply to you the customer. We keep it on the cloud, of course, and all the motors that are in the field will constantly update their parameters to this model in the cloud, so that we constantly can monitor the performance of the motor, the health of the motor. Very useful in fault diagnostics. And in future, we will do predictive maintenance. So as we monitor the motor, we know that something is wrong with the motor. We can send the technician saying that, time to go and fix it. Either the bearings are becoming bad, all the usual stuff. The bearings are becoming bad. Some seals are maybe broken. The windings might be getting hot for some reason, some short somewhere. All these things we can monitor and increase your customer satisfaction. And of course, constantly monitoring the motor will also give us an opportunity to constantly upgrade the software in the motor so that it always operates at an optimum level. So where can our technologies and products be used? Pretty much wherever motors are used today. Of course, EV is always a big market. H as we as a society or as a country as a planet we prosper, we continue to prosper, which makes the climate worse, and because of that we need more ACs. With more ACs we make the climate much worse. It's like a negative loop. So one of the ways to combat that is we need more efficient air conditioners. At least that way we reduce the carbon footprint of the air conditioners. Industries are always a huge market, and even all the consumer appliances like our mixer grinders, washing machines, we can all make them more efficient, saving a lot of energy and carbon reduction of the carbon footprint. So why us? By the way, just to be clear, there are a lot of people all around the world looking at rare earth-free products for the reasons I mentioned. So why us? We do have the game-changing IP, fundamentally new IP. We have this interesting business model about wherein we are not a manufacturer. We talk to the customer, understand his or her requirements. We build the motor and the controller, build like half a dozen units, give it to you, and you test it in your application. And then once you're satisfied, you can do the mass manufacturing. If you're not a motor manufacturer, we'll always hook you up with a motor manufacturer who can manufacture the motor for you. So we are more of a design company, but we don't give just designs. We actually give the products in low volume so that you can test it. And once you're satisfied, you can either manufacture it by yourselves or always go to third party manufacturers. And of course, we know motors well. Between the founders and the team, we've done a lot of motors from before, so we know quite well. And we also can expose an API to the motor, to and from the motor, because we build everything from scratch. There are sophisticated customers who would like to know more about what is happening inside the motor so that they can do a system level optimization. So if you look at a car, there are various subsystems, right? There is a battery, there is the motor, there is the actual vehicle with the load, and if we optimize all these three things, we can make the car run better, longer, faster, and all that. So for that, we can expose an API so that you can peek and poke into the motor. And we have a lot of domain expertise building motors. So these are our founders. The first one is me. My name is Bhaktha, and Rhythm already made an introduction. The one thing I would like to emphasize is that made in India for various reasons. We have not built products in this country, either hardware or software. We need to change that. It's not only a matter of pride; it's also a huge business opportunity, we believe. Ravi is our chief motor designer. He was the head of design in Kirloskar, the old big motor company from Bangalore and many other places. He's one of the few people you can count with the numbers of fingers in your hand who can design, build, and deploy motors, and he has done that throughout his life. Maha is our hardware and algorithm guru, power electronics. He is a graduate of IIT Madras and Rensselaer Polytechnic Institute, upstate New York. RPI is famous because and relevant because that's where a lot of the power electronics work was done in the 70s and even 60s. MOSFETs, IGBTs, they were all silicon carbide, GaN, they were all kind of invented and developed from RPI. So these are our list of customers. Our first customer is an HVAC customer. We are building a motor for them for one of the applications. We are building a motor for bounce. We are building a large motor for the Tata, and we are also built a 7 kilowatt motor which can propel a um, three-wheeler auto. This was done enabled by a grant from Indian Institute of Science. They gave us a grant to build a three-wheeler motor. They're not exactly a customer, but they funded the development. These are our supporters and backers today. We raised seed round about last year. Yeah, maybe 13 months ago, March of last year, from Kalari and CIIE, which is part of IIM Ahmedabad. And of course, as I mentioned, IISc gave us a grant. So I'll take a brief break here for maybe 30 seconds and let me know if you have any questions. Otherwise, I'll jump into the tech.
Shekhar, can I ask a question?
Yes, please go ahead.
Just maybe I'm probably jumping the gun here. This is just want to understand. I mean, one, you're actually changing the motor technology, or coming up with a, I would say untried or mainstream, not a mainstream technology. How is it
Yes.
going to affect uh, the associated components, like for example, motor controller,
Yes.
etc., etc.? So how is it going to affect? Would you be covering that?
Yes. So to answer your question, Shekhar, we are building the motor and controller together. And the controller by itself, it uses the same components as any other controller, a processor and switching devices and driver ICs and all that. So there is not much risk in the controller. So because we build and supply it, that goes with the motor we supply to you.
Okay, so that means the ecosystem associated with the motor, and those technologies will not need a lot of change.
Correct.
Okay.
Going one level deeper, so if as I told you, as you know, reluctance motor is just copper and steel, right? So it is somewhat similar in manufacturing practices, somewhat similar to an induction motor line. Induction motor is also copper and steel. So the existing manufacturing lines can be easily used for manufacturing the reluctance motor. If anything, manufacturing the reluctance motor will be simpler because of the absence of magnets and simplicity of construction. The induction motor has the squirrel cage problem, right? It's kind of sophisticated, but reluctance motor is ridiculously simple to manufacture. The complexity is in the software, in the algorithms, which we give you as part of the controller.
Okay. Thank you.
You know. All right.
And
So,
Mr. Bhaktha, I just have a question related to your the presentation that you've completed. It's Prashant Kumar. Uh, I think you mentioned one thing like your company is not directly involved in manufacturing of the product. Maybe in a very small scale, few
yes.
a dozen of thing you are able to provide it. So, is there any specific reason or some challenge that you faced in the industry because of which you are not doing it? So, just a question to understand.
Yeah. Valid question. A lot of people ask us. So there is some history behind this, and there are also business reasons behind this. So I used to work for Intel, the large microprocessor company, and I had the opportunity to spend a couple of weeks in ARM, ARM, the processor company from
Yeah,
UK, you're
yeah.
right. So I was heavily influenced by this one. ARM is exactly like what we are doing. They do the design, they do test chips, but the final chip which incorporates the ARM design and the final product is built by like 1,000 manufacturers all over the world, from
Mhm.
microwaves to servers to Apple, and that is reason number one. So we were heavily influenced by that. That is the history. The other thing is we want to be kind of asset light. We want to concentrate more on the technology and make it better and better, and kind of delegate the scaling of the deployment to our customers. So instead of we one customer, one entity trying to scale it up, if I make a deal with 100 people in the long run, the 100 people will deploy this technology at a much faster rate than us. That's
Yeah.
the thinking, that's the thesis. Um, and The last one is, as you probably know, I'll probably say something that is not usually liked by, in India, we still haven't built a motor and controller which is in production yet. Most of our, all our motors and controllers are imported today.
Mm-hmm.
And we want to change that. That's why we want to put more emphasis on technology. The other thing is reluctance motors is not the only rare earth free technology.
Yeah.
There is an age-old induction motor. There are people who say that a multi-phase induction motor with a VFD is also a good solution, maybe. Or there is more exotic technologies like rotating transformers,
Mm-hmm.
or even far into the future, um, there are electrostatic motors also.
Mm-hmm.
So, as a culture, we want to put more emphasis on technology than on
Got it.
manufacturing. Yeah,
Got
don't
it.
know,
Got it. Got it.
yeah,
Yeah.
don't know
Yeah.
whether it's
Yeah.
right
Yeah.
or wrong, but that's what we are planning to do.
No, it's a valid reason, definitely. Yeah. So thank you for the answer. So yes, please go ahead, Mr. Bhaktha. So we can continue your presentation.
Yes, sir. Okay. All right. Let me share this. So this is the more tech-heavy presentation. You can double clicking into the technology. So the electric motors are the engines of our every economy, not only the electric vehicles. The motors we need have to be energy efficient and with the controllers and have to be reliable. All these things are fine. So these are the kind of motors that are prevalent in the world today. They're starting from the top left, induction motor, well-known technology, works on directly on AC without a drive. If it is a three-phase supply or with a capacitor run and start like our ceiling fans and many other motors in the house. So they're extremely simple, very reliable, I should say. But the problem with these motors is they are very inefficient. They're about 60 to 70% efficient. A third of the energy we put in is wasted as heat, clearly not sustainable in the long run. So we have the BLDC motors. No, no, wait. We have the brushed DC motor. This is the one with the commutator. So according to us, this is the best motor in the world today. But the problem is that you need a commutator, and commutators the brushes wear away, and there is uneven wearing on the brushes. So this technology has been kind of out of fashion in the last decade or so. These were very popular before, but because of the commutator problem, they are not popular anymore. Then we have the BLDC and PMSM motors. They work horses today. They have the rare earth based permanent magnets in them. The way I look at it is BLDC is basically trapezoidal excitation and PMSM is sinusoidal excitation. So generally PMSM are more efficient, little bit more complex, and they are the main workhorses today. What we are concentrating on is switched reluctance motor and the asynchronous reluctance motor. Both have their advantages and disadvantages. So switch reluctance motors. This is the kind of the picture. I'll explain the picture. So the outer one, the dark green looking one is the stator, and we have opposite poles as one winding. So blue and blue, red and green and green. So this is a three-phase motor. There are 6 poles in the stator, and there are 4 poles in the rotor, the gray one. The gray one is the rotor. So if you and here is the way the synchronous reluctance motor works. Let me see if this link works. So basically, the idea in the reluctance motor is, we have the stator poles and the rotor poles. You energize when you energize these 2 poles, uh, the you create an electromagnetic force between these 2 poles and these rotor poles. So it gets pulled, and you can see that in the animation. It gets pulled. Now, as you start approaching the aligned position, the torque from that pair of poles is minimal, but you can see the next one has started producing torque. See, the next one has started producing torque. Now that torque is gone, and now it's picked up by the third one, and it goes so on and on. This is the principle of switch reluctance motor. Very simple. You keep switching the current in the stator windings according to the rotor positions. And as you can guess, there are many rotor stator combinations possible. This is the most popular one called a 6-4. There is 8-6, 12-10, 12-8, 24-18. Based on the applications and various other parameters, you can change the number of stator poles and rotor poles and make it work. So the rotor is just stamped steel. The stator is also stamped steel, and then there are windings. That means there is the construction is extremely simple, especially the rotor is just stamped steel and copper windings, and this winding is extremely simple. Nothing complicated like the sinusoidal winding you see in PMSM or induction motors. This is the reason SRMs are they have all the advantages. But the problem is, as you can see, the power delivery occurs in steps, almost like a petrol engine, or a diesel engine, where the power stroke is you get power stroke at when the mixture explodes, and the rest of the time it's freewheeling. Similar thing will happen here, leading to noise and ripple, torque ripple, and the because we are using only one pole pair at a time. The other poles are silent, as you can see from this picture. Uh, the uh, the material utilization is low, and that's why SRMs will be heavier or bigger. So this is the standard SRM. We have developed a lot of IP around this, which we can go into some more detail in some other talk, which fixes all these problems. So our motor is as power dense as an PLDC or a PMSM motor or close to it. And we have eliminated the torque ripple and the noise problem. I'll let this simulation run for some more time. And by the way, this was simulated on the tools we use. We have invested a lot in the simulation infrastructure. So this is how the SRMs work. So now going back. So the limitations, as I've mentioned to you, is torque ripple because you generate torques at discrete instants of time, which leads to noise and vibration, and of course, power density is a problem. So if you look at the top right, you can see the current rise and fall differently in different windings. But more importantly, you can see the torque bottom left. So you can see the generation of a torque, which occurs at discrete instants of time, and the end torque result, which is the bottom right, is this is here you can see the torque ripple. And some applications might tolerate it, most applications do not like this, and that's why switched reluctance motors have not been in wide deployment anywhere in the world. So that's why the current designs don't work. Low torque, low efficiency, low density, functional issues. So that's why there are commercialization challenges in switch reluctance motor. So we at Chara, as I mentioned before, we have come up with fundamentally new IP which fixes most of these problems. That was about switch reluctance motor. A synchronous reluctance motor is a little bit different. It's again copper and steel. Uh, it's again copper. This is the stator, the outer brown colored one. The rotor is, it does not have salient poles anymore. And I'll show you this simulation. and this will have sinusoidal excitation. So here you can see that we don't switch the windings anymore. We make three phases. We feed it with a three-phase drive. We set up the rotating magnetic field. It's very similar to three-phase induction motor, but not exactly the same. And the reluctance path in the stator always tries to align to the minimum reluctance path, and that's what generates the torque. Now, the advantage of SynRM, synchronous reluctance motor, is we don't have torque ripples anymore, primarily because of sinusoidal excitation. So the noise is gone, the vibrations are gone. The efficiency is still an issue compared to an BLDC or a PMSM motor. So these are the limitations of synchronous reluctance motor. So what we have done is to kind of combat these problems of SynRM and make it as good as a BLDC or a PMSM. We use a small amount of ferrite magnets if needed, which reduces the torque ripple and increases the efficiency. So ferrite magnets are this magnets, these are like the fridge magnets basically, very low power, and these are manufactured in India abundantly. They're manufactured everywhere. These are not the rare earth free magnets. So with this combination, you get the performance that is really, really, really close to the BLDC or a PMSM motor. Our motors are as efficient as a BLDC or a PMSM motor. So we're using the same technology. We built the hub motor for bounce, which we are testing both on the vehicle and on our dynamometers. So we already gone through this motor comparison. Will be as efficient as a magnet-based motor, but at a fraction of the cost. So these are the three motors we have built today, as of today. The fractional HP blower motor, and the 7 kilowatt light commercial traction motor, and the hub motor for SynRM, for bounce. So you can see that we are using both the technologies, switched and synchronous. It's always application dependent as to which one is better. We can't make a general statement that SynRM is better than SRM, or for that matter, any motor technology is better than the others. Every motor technology has its advantages and disadvantages. Induction motor is less torque, less efficiency. BLDC, PMSM motors have the rare earth issue, and so we are somewhere in the middle. Not in the middle. We try to be as efficient as a BLDC, PMSM motor, but without the rare earths. So we are doing other technologies, electronic gearing. One of the kind of suboptimum implementation of electric vehicles is that we don't use a gearbox. So that means the motor has to supply enormous torque at the beginning and has to be very efficient at the high end. It's possible, but if you have a gearbox, I think so if you have a gearbox and an electric motor in the vehicle, I think the motor will become smaller and more efficient. But of course, you get the complexity of gearbox, and we are trying to simulate that gearbox effect electronically. And again, people are trying this, and we have our own IP, and we have proven that our motors will have a lot of enormous torque at the beginning and more efficiency at cruising speed. And we are also doing a lot of research on sensorless control. That way, we make our motors more reliable and cheaper. The other things we are looking at in the future is so till last year it was all about demonstrating SRM, both synchronous and switched. So this year we'll be concentrating on the motor manufacture management platform and a AI-based design platform. So today what happens is if customers come to us, we listen to the requirements, and Ravi and his team, based on their experience, start designing motors. We want to make this more automated, more optimal using AI and ML techniques so that we come up with better designs. And in the long run, maybe 3 to 5 years from now, we hope that this design, the CI-based design platform, will come up with designs which even we have not thought about. We will look at newer materials in the future, which makes the motor efficient and cheaper. Newer hardware architectures, silicon carbide and GaN. So today we are using either MOSFETs for lower power, lower voltage, and IGBTs for higher power and higher voltage. And in the future, we'll start looking at custom silicon, because today all the silicon that for motor control is optimized for BLDC or PMSM. And I think if we do silicon which is more tuned or matched to the needs of SRM, we will bring in some efficiencies, both cost and performance. And far into the future, we will look at other technologies like hybrid or the more exotic things like rotating transformer or even electrostatic motors.
Thank you very
Patient.
much, sir. Thank you very much for supporting this program. And first of all, we wish success for Chara Technologies and the whole team. And definitely, we believe that the aim of goal of bringing a complete Indian-made product
Yes.
for the global global industries.
Yes.
That's definitely a good insight. So thank you so much for sharing your thoughts, and thanks all participants actively engaging and asking insightful questions. So thank you everyone. Yeah, thank you all for joining.
Thanks, guys. You guys have a good weekend. Thanks. Bye.